So I'm going to talk about management. I'm going to talk about distributed management. And the story is that management changed a lot over the last 20 years. 20 years ago, the discipline of management was essentially created. There was a time where SNMP got standardized, for instance. Who knows about SNMP? Oh, very good. Of course, the veterans know, but so this was a protocol that was essentially standardized at the inception of the management as a discipline, also in academia. Okay, it's still in use today, and actually has a lot of advantages. And so, but since then, a lot changed. Two major things happened. In the 90s, the services essentially which were scheduled to run on broadband networks, these telecom services, they were eventually run on the internet. So it was a big change. And then later we found out that actually the internet architecture has some shortcomings that prevent us from pushing these services further. And this is why people work now on the future internet, and the whole summer school here is about future internet. And all this development also have deep influence on management. How we manage this system, what our idea is about managing network systems, and so forth. And some people are involved in this journey, so myself, and I see there José from UPC. He's also in the network management research community. And I'm going to talk not about whole management. I'm going to take a slice out this afternoon, talk about distributed management with the goal of making management systems scalable. With scalability, I mean up to 100,000 nodes, something like this. Scalable, and make them react much faster. Today's management system on large network, they react on a time scale of minutes. I should say yesterday's. What we need today are management systems that react on a time scale of seconds, even in a very large system. Okay, so this is very clear that we need new technology. And I'm gonna slice something out for you this afternoon. Okay, so why did we get here? What were the drivers of the last decade, the last couple of years? So we have new requirements for management technology, increased scalability, I mentioned already. The networks or the network systems today are much larger than 10 years ago. We have much more elements, we have much more users, we have much more services, so everything is larger. They also need to be more robust. Business critical applications run now on ICT technology, so will societal critical applications. The systems are generally more complex 10 years ago, so you need some level of self-configuration. And as I said, you have to decrease very much, from a management point of view, the reaction time of a management system. New technology emerged, you see them here, and also new actors. 10 years ago, who demanded management technology? They were the big operators and the big computing companies like IBM. Now we have a completely different picture. So we have strong internet companies who are driving essentially. The interesting stuff in management happens right now, not necessarily with the operators. Okay, Google, Amazon, I forgot Facebook, and also other actors that came up now, like Microsoft and Apple. They all run large infrastructures. They run data centers with 500,000 servers. Now manage this thing with SNMP, you can't. Can't. Okay, unfortunately we make some progress and there are enablers here. Since I'm going to talk about distributed management, there are advances in distributed computing. There are new protocols. There's an understanding, for instance, today are people working on this, that we understand how distributed protocol execute on changing infrastructure, on a changing network. It's very important that we understand this. And so people are working on this, and this drives us forward in terms of management technology. Then the enablers in terms of network programmability, we see now that hardware manufacturers, they more more and more open up their interfaces so you can actually bring management code directly into the network. And you know there are new initiatives, OpenFlow and software-defined networking, and I would hope that you have heard something about this over the last couple of days. So these are enablers of new approaches to network management. Okay, so what is the goal of what I want to talk to you? I want not necessarily go very broad, but I want to go a little bit deeper than the talks maybe you might have heard so far. So I want to focus on two classes of tree-based management protocols which are truly scalable, two families of these protocols. And I'm going to describe them to you and what you can do with them. And also, what's important, I'm going to discuss the fundamental algorithms that underlie them. Because if you understand those algorithms, you understand the properties of these protocols. So this makes a system predictable. You can say to which extent the system is going to scale or not, for instance. Okay? And then once you have this protocol, you can refine them to do a certain job for you, do a specific job for you. And I will also like to show to you how this can be done. Okay? My understanding is you have the slides of this lecture, and you also have a document which essentially it's a report that describes in a little bit more detail what I'm going to say. Okay, I'd like to extend the report in the next couple of months, and here is the URL where you can download an update if you're interested. And if you find mistakes or errors in the old report, let me also know so that I can correct them. Okay. So here is to the methodology. I said I'm going to talk about two classes of protocol today, which are useful for network management or generally for management of network systems. The first protocol is the echo class protocol. The second class protocol is the GAP protocol. They are somehow related, you see, but they solve fundamentally different problems. And what's nice about this protocol is they are full protocols, but from an application point of view, they're still skeletons. Nice about them is you can write them on a page. And so you can look at them and you can understand what they're doing. Okay? But then if you like to really use them in the operational environment, to do let's say for real-time monitoring or for detection of textual crossing, you have to instantiate and sometimes to extend them. Okay, and then you end up here. These are the problems which essentially you run them in your operational environment. Okay, so these are, if you want this, they might also be adapted. For example, if you have a protocol here, you write them on a cloud infrastructure. This is going to be different software than if you run it in a sensor network. So you have to make certain adaptations, okay? But again, we're going to focus mostly on this. Now, this protocol has certain properties. These properties come from distributed algorithm, which are put together to give us this functionality. This distributed algorithm, they were not designed for, we're going to discuss maybe 3 or 4 of them today. They were not designed with management application in mind. These were designed by theoreticians 20 years ago, 25 years ago, to solve certain problems in distributed systems like synchronization or tree construction or self-stabilization. But we're going to use this to give our protocols certain properties. So you see here how essentially what I'm doing here is not only to tell you how I want to construct this lecture, but I also tell you specifically the PhD student how you should develop your functionality. Because in principle, we are all practitioners. All of us want to solve very specific practical problems. So we want to solve problems here. And the problem, the mistake many researchers make is that actually they stay here. They go into the specific technology. They say, aha, this is my problem. Aha, this is how I can solve it. They come up with something. And the protocols here are way too complex to really be analyzed. So then essentially you do a prototype, you test the thing, certain things does good, certain things does less good, and then you fix it. What we as researchers should do, or you as a PhD student should do, you should say, yes, this is an important problem, you know. What is the generic version of this problem? What am I generically trying to solve? And then you are here. This is much more compact. You can write this much more concise. And then you should ask yourself, you know, how can theory help me in proving something what I'm doing, that it actually has the property? For example, if you're very interested in very large systems, then you need to know how something scales. Otherwise, there's no way. Okay, so you go back, for example, into algorithm and see which algorithm can help you. Okay, so this is what I'm saying is this is not only how I want to talk today, but also it has to do with research methodology essentially. So good research in which has a lot of depth essentially goes the whole thing. Application oriented researchers like us, they tend to stay here. Theoreticians tend to stay here. And so there's no bridge. The bridge is very difficult. Okay. So this is the outline. I mentioned that I want to discuss two families of protocols. But before I do that, I have to say something about architecture, how the system is structured, what are the components that essentially execute these protocols. And because we need to understand that to get the context. So I'm going to talk about what ideas people have to distributed management, and I'm going to highlight a very simple architecture for peer-to-peer management where these protocol families are actually going to run on. So these protocols here are going to run on this architecture. And you're going to see the architecture is very generic, so it might also fit into your system. Okay? As I mentioned, this is should be interactive. So I want you to ask me questions or make comments. And maybe I ask a question now and then myself and hope that you help me. And I have a lot of material. There's no problem if we do not finish, because I have to have written this thing up anyway in the report. And for those of you who are interested, you can finish this thing. And basically, this thing has 3 parts. This is the architecture. It takes 10, 15 minutes or so. And then this is something, in principle, these are 2 topics that can be independently studied. So if I only finish with the echo, that's fine. Fine with me. If you learn, I want that you learn something. Right? Okay. So if we talk about distributed management, first we have to understand what decentralized management. This is traditional management architecture in its simplest form. And most of the management solution operation today follow this architecture. Also you find this architecture also exemplified in SNMP. Okay, so in the simplest form, you have a management station here. This can be a server. This can be distributed even. But in the simplest way, it's a server. And you have nodes. If this is a network, this can be routers or switches. Okay? Now, where do you manage? You do management here in this program. There's a management program here. And the way we do management is we read information out from the network. The way we do this is we read information from managed objects in these agents. Managed objects are abstractions for management purposes on operational data like link utilization or configuration data. So what this program P is doing here, it reads these objects and writes certain objects. Okay, this is from an architectural point of view what management does here. Note that the program actually runs outside. So this is the managed system here. So the management program runs outside the system. And the interface is normally very low level. Essentially, it's reading and writing objects. So this architecture, which is simple, although has been very successful for small systems, okay, has two characteristics. The first is the management intelligence outside the network is here. The agents are normally dumb. We call them dumb. in terms of service, they may be very sophisticated, but in terms of management, they're normally dumb. Okay, and so this is the first thing. The intelligence is here. The functional complexity is outside. Okay. The second thing is if you look at the interaction pattern. So there's a management station here, and which interacts in this kind of a star pattern with agents. Specifically, the agents, they do not interact with each other. So it's a very simple interaction pattern. Okay. Now, this thing has two drawbacks, two inherent drawbacks. The first is obviously there is a single point of failure, no? Single point of failure. So if this thing dies, no management. Okay. What people normally do is you bring in redundancy. So you don't bring in just one station, there's another one. Okay, and then you have some problems in synchronizing and making sure that always is clear which station is. But then you, in principle, from a practical point of view, you have approached the robustness problem quite well. So that can be solved. But there's another problem which is not solvable in this thing. These systems are inherently not scalable. Inherently not scalable. How can you see that? Let's make a simple example. So we want to find out what is the average link utilization in my network. We have a management component that runs here. Would like to find this out. What are you doing in an SNMP network, for instance? You poll all the nodes for the utilization of the adjacent links. No? Poll, bring them together and compute it. Okay. Now let's just think of what's happening. Oops, where is this now? Huh? Yeah. Okay. Now let's look at this operation and the three simple metrics regarding this operation. The first metric is the management traffic generated, and we can exemplify that by the number of messages sent between the management station and the nodes. The second metric is the load on the management station. Okay, and we can measure that, for instance, by the number of response messages that are processed by the management station. The first is how long it takes to execute this operation. So we have these three metrics. And you can ask yourself now, how do these metrics change when I increase the system size, when I increase the number of nodes in the network? And what you see very quickly that all these metrics, they grow linearly with the number of managed nodes. I wrote this here as an upper bound with your notation. And that's true for many management operations and for many others. Let me see here. Yeah, these two metrics they can even be exponential for certain routing problems, for instance. Okay, but what this tells you is the following. What the following: if you increase n, the number of nodes, at some point, the communication link to the management station is going to be full. I cannot tell you whether it's with this coarse model, whether it's with 50 nodes, with 500 nodes, with 5,000 nodes, 5 million, but at some point this link is going to be full. It's going to tell you at some point the management station is going to be overloaded. And it's going to also tell you at some point it's going to take too long for this operation, for you to wait. So you see. So this is what we mean by the centralized model is inherently not scalable. There comes a point where this system, this architecture is not useful anymore. Now, in practice, this happens between 1,000 and 10,000 nodes in real scenarios. If you go beyond that, you need to do distributed management. And as I just gave you the example of large data centers today, which have 500,000 servers. So you need a distributed solution. Yes. 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 Right. But fine, if you don't like that, take the load. Right. So you can, for example, if this is, let's say, if this is a sensor network, then this might be very important. If it's a sensor network, but I just wanted to give you. You're of course correct with your argument. What I'm saying is, I give you 3 metrics, and you pick the one you feel most appropriate for technology. The only thing it tells you, you're going to have a problem if you increase. And this problem typically shows up with between 1,000 and 10,000 nodes. Okay, so thanks for the question. Thanks for the first question. Okay, so of course, people have thought about this, and over the last 20 years, they come up with different approaches, and I listed here a couple of them. So of course, you can, instead of a one-level hierarchy, you can have a hierarchy with several levels. Okay, and that works as long as your system configuration is relatively static. Once this thing is changing around, then you have to adjust, and that's going to be a problem. Then script-enabled agents. Let's look at this solution. Okay, you see now with the script-enabled agent, it looks like this. I have the management program here, which downloads the script onto an execution environment on a router, for instance. Okay, and so some of the management tasks can actually be delegated to the devices in this case. This is also why this approach is called management by delegation. And for certain tasks, it's actually quite efficient. Let's say you want to have an alarm whenever a link utilization goes beyond 90%. If you do it the classical way, so every 30 seconds, you poll all your devices, then you might find this also out. But having a script executing, let's say, every second on the device and sending you an alarm if this happens is more effective and also efficient in many ways. Okay, so that's one possibility. Another possibility. Here you see. So some of the management capability, some of the load is moved down to agent. Of course, you have to pay for that. You pay for that by having execution environments here. Okay. But you see, the interaction pattern is still the same. There is single interaction between the management station and these boxes here. Okay. Now, people have thought about one step further. Okay, so this is called mobile agent. So not only download I a script or program here on this mobile agent, but this program can move within the network, can hop from one node to another node, okay, according to some itinerary. And when the operation is completed, it can report back to the management station. So think about you want to do some a maintenance job. You delegate it to the program goes on a nation, performs maintenance there, hops to the next, hops to the next, hops to the next, hops to the last, and reports back. Okay, so that was the idea of mobile agent. And in mid-1990s, this was a very sexy research area. A lot of people working on this. Sean, did you work on this? Okay. How about Benoit? Did you work on mobile agents? No. Okay. I have to say, it turned out to be a disaster. Mobile agents. So script-enabled management is still is done today. Mobile agent not. And there are two reasons for that, and I have them on this slide. The first reason was people wanted to have too much. They thought mobile agents were essentially representative of the network administrator, so that they were very complex programs who had a lot of intelligence, and they were essentially dispatched into the network to do an administrator's job. That was the idea, at least of part of the community, the way they wanted to go. Okay, and that turned out to be just very complex to do. So you need a lot of AI, and you need a lot of supporting devices for that. Okay. The second problem was, so you send your mobile agent now on your node who does some stuff, and you made a programming error. Okay. Now the guy is dispatched. Huh? Now this agent can screw up your network. And so there's a safety issue, then of course also a security issue. And so this is why at that time operators were very reluctant to look at this at all, because for mostly the last problem, but also the first problem, the complexity was an issue. So mobile agent, they did not succeed in terms of deployed technology. I'm not sure, Sean, you would agree with me, but I think niche applications these days. Okay, so this is the architecture essentially I wanna promote today for distributed management. The new thing is this management plane here. Management plane, this is the conceptualization of the management resources in the managed system here in network. So the idea is that each device here, or each managed node, if you want, has an associated managed resource with computation, memory, and storage capability. We'll call this a management node. And this node knows about neighbors. So this is a neighbor of a node. This is a neighbor of a node. So you have a neighbor relationship. And now, once you have a neighbor relationship, this induces a graph on this thing, which I call the network graph. As here, you see a grid topology can have any topology you want. Okay, and now, what are management protocols? Distributed management protocols. Distributed management protocols are protocols that execute on this graph. Execute on this graph, they read state variables, and they set configuration variables in this system. So that's the basic idea. Okay, so how can I realize this thing in a real system? There are at least three ways. Number one, this can be a virtual machine running on the CPU here. You might have large switches, if this is a router, large routers that have special hardware, so-called blades, which you connect to the backplane, and on those processors you can run such a management node. Or it could also be that it's a standalone device, a network appliance that is maybe physically near such a device. So this is how you can realize these management nodes in a second, and this network graph you could realize, for example, by an overlay. Ramon.
Does any node in the managed system has a sort of equivalent in the management plane, or do you make a selection of those nodes which are?
Okay, so right. So you're saying, is there a one-to-one relationship or one-to-many relationship? Both is possible, of course. With the implementation we have done, it's always a one-to-one, but I can well think that in a real system you have a one-to-many.
If you have a one-to-one relationship, how do you manage the scalability issue?
If you have a one-to-one relationship, how to manage the scale? So
you need a number of nodes for management that you need nodes in your network.
right. There's nothing wrong. There's nothing wrong with that, because this means the management capacity grows linearly with the number of network elements. The question is then, of course, how. And you're going to see the algorithms which we are going to discuss here. They are correct in for any kind of network size. But you have one point, which means this management plane obviously has to be constructed and has to be maintained. And it is probably easier to have a relatively small plane than have a relatively large plane. Yes, you're right. You have to manage the management plane. Yes. By the way, these are concepts from Forward. This is Right. But I still think this is the way to go. Okay. So yes, I think this is what I just narrated, and you just find it on the thing. Okay. So here I put everything together just as an overview. So centralized management is the most simple solution. And I have to say, if you have 5 nodes, this is the way to go. Okay? And if for decentralized, you have script-enabled agents, which has generally low complexity in the script, and it's also successfully deployed today. You have mobile agents, which I think didn't make it as a technology, and you have this peer-to-peer management, which allow you, as we're going to see, increase the parallelism tremendously, and have, in terms of code executing in the network, the complexity of the code is relatively low. And I'm quite sure that this architecture, or some version of it, we're going to see in future networks. Yes?
When you are saying peer-to-peer management, you don't think about any kind of hierarchy between these peer nodes, or are you thinking in a pure relationship?
Right, right. Okay, so you're saying your question is the following: from an architectural point of view, are they all flat, or is there some structure behind this thing? Maybe a hierarchical structure. And I have 2 answers for that. The first answer is you're going to see then the protocols I'm proposing here for doing monitoring and configuration. They're going to be tree-based protocols. Tree, it has inherently a hierarchical structure, so we have a hierarchy there. And but that hierarchy is flexible and adjusts itself. So this is the first answer. The second answer is you're correct in the sense that this very simple architecture here is an architecture for a single domain, a single authority. Now you can ask yourself, if I have if I'm in a multi-domain federated environment, how can I extend that? I don't discuss a solution to that. Right. Okay. Right. So now let's start with the first protocol family, which I call echo protocols, and you're going to see then why we call them echo protocols. And I just let you read yourself here. This is what they can be used for. And this describes essentially how the protocol executes on this management plane. There is one node where the protocol starts and ends execution. We call it a root node. The protocol execution can be understood as a wave that expands and contracts. There are going to be local operation executed on the nodes when the wave expands. And local operation, obviously, they have results. Every operation has a result. And you have to collect the result, and the results are collected and aggregated inside the network to the final result, which is then available at the root node. Okay, I want to show you an animation of such an execution of echo. Right. So you see here the management plane from above. You see management nodes. You see the network graph. And I'm going to start the execution of this protocol here. I could also start here. It's just nicer to look at if I start here. So what's happening during execution is the following. So this management node sends messages to all its neighbors. These messages arrive here. This message arrives here and gets executed and triggers a local operation, plus messages to neighbors are sent out. And so on. This message here arrives here, gets processed, and message to its neighbors are sent out until the whole domain of where this protocol executes is touched. Okay. Now here, a leaf node performs an operation and sends an answer back. This is one here first. Okay, the answer messages get interpreted. I have two messages here coming to this node. They get interpreted here, and the answer is going to be sent up. Okay, so let's go through once again the execution here. I said, did I say, the protocol during execution creates a spanning tree. Let's see how this works. So a message are sent out here, and the first message that any node receives marks that the receiver of the message as a child, and the sender of a message as a parent. You see here, and once the child-parent relationship is established, this thing becomes green. So this is going to be the parent of this node, and this now you see it's going to get a message from this guy. So that's going to be a child from this, and so forth, and so forth, and so forth. Okay, you see these messages here. This message comes from this guy, and receives this node, but this node has already received the message. So they're not going to be in any relationship on the tree, okay? But this guy is going to be the child of this node. Okay. So you see, this is the way during the execution of this protocol that the tree is constructed, a spanning tree. Okay. Is this a BFS tree? What do you think? Actually, I have to tell you something else. I have to say, the way I execute this protocol here is misleading, because I execute it as a synchronous protocol, like in a synchronous system, you know. So everybody moves one step, moves one step, moves one step. Now, this distributed synchronization is very expensive. You don't want to have that in a network system. Okay. So you want to run this asynchronously. And I just showed you a synchronous execution because it's easier to analyze. Asynchronous would mean, you know, you might have contraction on one end and expansion on the other hand. So it's difficult to really see what's going on. Okay, this is the protocol we're going to look at. Is a protocol is a protocol for asynchronous execution. Works without synchronization. Yes, Daniel. Almost. I think the question what I'm asking is a better one. What can we say something about the topology of this tree? You know what a BFS tree is, no? A BFS tree is a tree where on a graph where each node has the shortest path to the root. The shortest path in terms of number of hops. Okay. Now, if I execute this protocol in the informal way I just said, is this going to be a BFS tree or not? Yes, please. Another question. Okay. Exactly. So generally not. Generally not. It depends on the delays in the network. Yes. Yes. And so, but the only thing the protocol makes sure it's going to be a tree. But the form of the tree is going to depend on the delays. Yes, sir. Yes. Okay. Okay. By starting underlying algorithms that have been proven to be loop-free. I'm going to come to that. I'm going to come to that. And I'm not going to prove that they are loop-free, but I'm going to refer you to literature where you can read this up. So this protocol is loop-free on any topology you can think of, as long as it runs on a connected network graph. The graph has to be connected. Okay. Yes?
In any case, what's the purpose on sending messages this way? Because you want to retrieve the state of all the other nodes.
Right. Aha. For what you're going to, I'm going to discuss then what we can do with this thing. One thing is yes, for global state estimation. Yes.
You want to know the state of the nodes in the neighborhood.
Yes. Yes. This is one possible. There are more applications for that. That's one. But I'm gonna list them what I can do with it. Yes. It's a mechanism. It's a mechanism. Right.
How do you know when to stop a message that going back and you bring it back again? How do you know?
This is the magic of the protocol, the magic of the underlying algorithm, which I'm going to discuss in a second. Okay, so let me go back here. Right. So now I didn't come up with this thing. This is there are class of algorithms of graph algorithms behind this. They're called echo algorithms, or more generally wave algorithms. And before going into discussing them, I just have one slide that shows the assumptions which we make so that we can reason about this algorithm. Okay, so these algorithms, they execute on a network graph, which has bidirectional link, and is a connected graph like this one. Okay. We assume that each node on this graph has a unique identifier. From a practical point of view, that's not a problem. Take the IP address in a network, and then you have an identifier. These neighbors on this graph, they exchange messages. The message has a type. We have seen two types of messages, echo messages and explorer messages, and can also have instantiated arguments. So variables can be exchanged if you want. Okay, and we assume there's an execution, an asynchronous execution model behind this. So events in this system can happen at any time. So this guy can send a message at any time. This guy can process a message any time. The only thing we assume that the delays are bounded. So it takes a certain amount of time to send a message from here to here, and this cannot be infinite. Okay, so then we make sure that these protocols terminate in finite time. Okay, so the question is how can we come up with a correct protocol that exhibits the behavior I just showed you, exhibits that synchronization and communication behavior? And it's actually quite simple. So this is the algorithm. This is now an algorithm. This is not a protocol. It is a theoretical algorithm that has been developed by Segal in the 80s. And this person was studying distributed synchronization, and actually published this algorithm in the transaction of information theory, which I found very, very astounding. Okay. And I adapted it somehow so that we easier can relate it to the protocols I'm going to show you. So, how does this algorithm work? There are two message types defined: explorer and the from variable, where the send ID is filled in, and echo. Every node initializes a variable n with the set of its neighbors. Okay, right. And then we said there's a special node, the root node, which executes this program, and all other nodes execute this program. That's going to be it, very simple. So let's see whether we understand this. Okay, what does the root node do? The root node, for all n in n, this means for all neighbors, it sends an explorer message with the sender root, of course. So this is the root here. Okay, sends a message to all neighbors. Then it waits for echo responses. And you see in this while loop, it receives a response from each of its neighbors. So while the set n is not empty, it receives a message from neighbor n and takes that neighbor out of this neighborhood set and loops until n is empty, and then the operation is terminated. Okay? Every other node waits for an explorer message. It also has initiated the set of its neighbors. Okay? When the first explorer is received, a parent variable is set to that address, and that neighbor, meaning the parent, is taken out of the neighborhood set. And then it sends a message to all neighbors except the parent. And then it receives a message from all neighbors. After having done that, it sends an echo back to its parents. Okay, so for example, this node here receives a message from the root, and since this is the first message explorer it receives, the root is going to be the parent of this node, and then the node sends a message to all other neighbors. Same this guy here. Gets a message from the root, sends a message to all other neighbors. Okay. Now look here. Okay. If you have paid attention, you can tell me why I say here receive an exp or an echo message. Why not just an echo message from other neighbors? It's asynchronous, yes, but still. So this means, again, there's a message coming to a node. The node takes the parent out of the neighborhood set and leaves everybody else in, and sends a message to all of them. And now receives an answer. And some of these answers come as echo messages, some of them as explorers. Why explorers? Right. I think, right. Look, this is exactly the situation we have here. So these are two nodes. They send messages to all the neighbors. Okay. These neighbors are probably going to be children of this node. They're going to send an echo back. But this guy has already received the message from the root and sends now an explorer to this guy, and this guy sends an explorer to this guy. So they send each other explorers because they are neighbors on the graph, but they are not in a parent-child relationship on the tree. Is this what you wanted to say because that's the correct answer? Or did you want to say something else? Right. Okay, so the question is, of course, you say, okay, in principle, these messages, they are not needed. They are not needed. And why then sending them if they are not needed? And the answer is because these nodes, they only have local knowledge. Okay, they don't know that this might not be a child. They don't know that this guy is already a child of the root and cannot be in a parent-child relationship with this guy. So they don't know that. They have only local knowledge. They only know these are my neighbors. You see, in this algorithm in principle is a global algorithm. You can do global tasks with this algorithm, but each node executes only on local knowledge. The only thing it knows is the set of its neighbors. These are my neighbors. Yes? Right, this is a good question. In the theoretical algorithm, the root node is defined at the beginning. You see, there's one node called root, and that root node executes this program. So in the theory, this is defined. Everybody else is this. Of course, in the real system, you want to change this, you know. You want to change. You don't want to have but here I'm talking theory. Okay. Right. Let me just take. What did I want to say? Yeah. And why this person got this paper published in this transaction journal, prestigious transaction journal, is because it could, at that time, it could prove that this algorithm here creates a spanning tree. Where is this tree? You see the tree is actually encoded in these variables here. The parent variable encodes in a distributed way the tree, the spanning tree. Okay. It creates a tree. It terminates. And what one can also prove, this is actually quite easy to see, that if you execute this algorithm, then during the execution, every node, the root node or any other node, to each of its neighbor, it sends a message, and from each of its neighbor, it receives a message. Okay. In terms of messages in the network, this means I can take any link in the network, and during the execution of this algorithm, two messages cross the link in each direction. And this can be proven for any topology. So this is what the algorithm does. Right. Now the thing is now, this algorithm, what can we do for management? Because it does nothing. The only thing it does is a distributed synchronization. How can we use this for management now? So we have to, somewhere we have to bring management semantic into this thing. Because so far what we have is a global operation. Every node is touched, every node does something. This thing starts at the root node and ends at the root node. Now how can we do something useful? And let me just ask you here. I can extend this algorithm easily to count the number of nodes in the network. I can extend this program easily so that it can run, count the number of nodes. And you say this is trivial, but think again. This algorithm runs without any global knowledge. It just executes, starts and ends, and can give back. And in today's large networks, inventory management is actually it's not a straightforward task. You know that the time have passed that you go into a network administrator's office and that person has a nice map from his network on the wall. Today, that person doesn't know anymore. You know how many devices it has. It needs a program to find this out. Okay, so PhD students, I want to have this thing extended so it gives me. It counts for me the number of nodes in the network. How can I do that? Daniel knows. Okay. Okay, so
Then you had the echoes that are in the echo plus the water.
okay, so where do I, so here I have to add another argument. This is what you're saying. Okay, that's true. That's true, but you need to do more. Because you have to instantiate that and you have to process it. What more do I have to do? Correct, what you're saying is correct. This code, how can I extend this code that actually counts the number of nodes? Here. Right?
You add the argument that you're receiving from the echo plus if it's plus 1 because it's
Okay. That's not sufficient. That's not sufficient because this echo might come back. You might, oops, shit. You know, the echo comes back here. And what this echo should report to you, essentially, it's the subtree, the size of the subtree. And how do you accumulate this? Okay, so this is a leaf here. Okay.
for instance 1 because it's only itself.
Right.
And then this 1 will have to wait until it receives everything.
Right. But so this means you need a state variable here. Okay, so you have to define a state variable, and you have and when this thing reports back to its parent, this time the root, it has to read out the state variable and send it back. Okay, that's basically how you do it. Yes, 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 yes. And so you're going to see, and we're going to create a much more complex abstraction of this. Yes, that's correct what you're saying here. Okay. So you see this. What this protocol gives us, what this algorithm gives us, essentially the communication behavior. What's missing here is the management semantic. What I actually want to do with this distributed operation. Yes. Right. 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 Okay. What's the difference between this and flooding? Right. So you can say there is. I agree with you. There is hidden flooding in this algorithm, but this algorithm does more because it not only expands, it also contracts. So the synchronization part is the added functionality here. We would have to look into that. Maybe they are actually based on echo. I mean, this is a class of algorithm. They're called wave algorithm, and echo is essentially it's a subclass of this algorithm, which are called PIF algorithm, propagation with information feedback. I'm not saying this is a very old algorithm. I'm not saying I'm showing you here something completely new. What I'm showing you, the new stuff I'm showing you is how you can use well-studied, traditional, distributed, well-researched, well-understood, traditional distributed algorithm for distributed network management. This is the new thing I'm showing you. So it could be that your specific flooding algorithm is actually based on echo as well. Yes, ma'am. I'm developing this later. Ask me in 10 minutes. Yes?
So each node would send an echo message and the reply to an expo message, right?
Each node would send. No, that is not necessarily true. Echo messages are only sent to the parent. You see here, in this case, I show you here the tree. I have to be very careful. The tree looks here like this. Okay. So echoes are always sent, explorers are sent out from one node, but echoes are always sent from the child to the parent, from the child to the parent, from the child to the parent, and from here to here. Between these two nodes, only explorers are exchanged.
My question is, for a child to the parent, would send only one echo message, or during the time it has to send a couple of echo messages?
No. Only one. During one execution of echo, the parent sends one message to the child. You'll see this here. This is the root node for all neighbors of the root node, for all children of the root node. There's one message sent. And then the root node goes into listening mode and only listens for echoes.
So when I'm trying to count the nodes, since this network, I've learned that through counting the nodes of the network, each node starts to reporting the number of its leaves, number of its child
Right?
to the parent.
Right.
How can we be sure that we're not going to discover a new child after sending a report to our parent?
All right. This is the properties of this algorithm. The properties of the algorithm make sure that each child is only reported once. That's the only thing I can say. It's a property of this algorithm. Maybe during the break we can sit together and look at it again. Okay, so now we extend this. We have the communication behavior. Now we want to make something useful for network management. And the question is, how can we extend this now for network management? Something which we need has already been brought up by the lady over there. And in principle, we want to be able to start an echo operation on any node on the graph, not just on a predefined node. So the root node has to be flexible. Okay. Then we want to do local management operations on the nodes. We discussed a very simple local management operation, which essentially count one. But of course, one can do much more on a node than just count. Okay, and then these local operations, they have results, and we need to aggregate these results, bring them together at the root node. And for all of this management functionality, which we can say this is the management semantics of this operation, we create an object. We encapsulate all these things into an object, and we call this object the aggregator object. And so you see now how this thing works. So we have this generic protocol, this generic algorithm, the echo algorithm. We take this aggregator object, which has the managed semantics. We put this thing together. And now we have a distributed protocol that does what we want. Now, you as a developer of a distributed management application, you take this echo. Okay. The only thing you have to write is an aggregator. And then the echo algorithm guarantees you correctness. That's the idea. Yes?
Problem that whilst we are doing the contraction,
Uh-huh.
before ending the contraction phase, we start a new expansion phase from another node. Does it make sense?
This makes a lot of sense. And I'm going to show you now an echo protocol. And this echo protocol is based on the assumption that only one echo execution takes place in the system at a time. And the reason for that is that the code is very compact. And as I mentioned at the beginning of the lecture, or at the early stage of the lecture, I'm going to show you a very simple generic form of the protocol. If you want to run this protocol in a real operation environment, you have to make several extensions. One of the extensions is that you can allow for multiple invocations, of course, as you mentioned. And those extensions are not so difficult. I'm gonna list them, and the ones you mentioned is one of them. Of course, Sean, you might have a problem if, for example, both of these echo protocols actually make changes to the network, and then essentially you have a problem which you have to solve. Okay. It is now 4 o'clock for coffee. Can I show you the echo protocol before we go? And then we discuss the property when we come back. That's okay. Okay. So it's not difficult. It's not difficult. Okay. So you see, these two, instead of a two-message type like the theoretical algorithm, we have four message types. The explorer we already have. Now this echo we have extended with an argument specifically for bringing back the partial results, the same as when we are counting. Okay. The fact that echo can be invoked on any node of the network, we solve by two new messages. Invoker can be a management station that sends its invoke message to a node, any node on any management node, and that management node starts an echo. And this is for the result. We need an aggregator object, and this which captures the management semantics. So here we have the local operation that is triggered on the node. We have the aggregation operation, which tells us, how to aggregate the results that come back from this tree-based operation, and this just gives the value. This is something which I'm going to talk about later. Okay, and so this is now the protocol. The node initializes with a set of neighbors n, which we have. Visitis tells us whether the node has received an explorer or not. Okay, and then essentially it's about interpreting the messages, these four messages that come. Right. Let's just look at maybe the invoker which becomes the root node. So a message is sent from a management station, say, to one node. That one node runs initiate the local operation, and then sends an explorer to all nodes. This is what the root node does here. You see? And it says here, if the neighborhood set is not empty. What is the case if the neighborhood set of the root is empty? Is there only one node in the network? So it's not terribly interesting, huh? But we have to catch the case. Huh? Okay. Then I say here what's happening with when I process an echo message, and what's happening here when I process an explorer message. Let's just look at that. So the node comes, the message comes, and the send of the message is taken out of the neighborhood set. If this node has not been visited before by an explorer, then we establish the child-parent relationship. Okay, we run the local operation here. Okay, now if the neighborhood set is empty, this means if the node is a leaf node, then an echo is sent back. Otherwise, the explorer is sent back to the neighbors, except with the exception of the parent, which has been taken out. Okay. This is maybe interesting. What's happening here? So I get an explorer and do nothing is exactly this case here. Exactly this case. Because echo is a tree-based operation, and if I receive a message from a peer on the graph, but not a peer on a tree, I do nothing. Okay, so that's it. So we have a distributed management operation, and the only thing we have now to do is trying to find out what are the properties of the protocol and how can we use it. How can we use it is what kind of aggregators can we write. The managed semantic is these aggregators. If you want to write a management application, you have to write an aggregator. This is a very simple example of such an aggregator. And this aggregator computes for me, or determines for me, the link with the maximum load in the network. So what is the load, and what is the ID of this link? This is what I want to have, and this is the state of the aggregator here. What I have to write to run this thing on an echo-enabled environment, if you want. I have to write the local operation. I have to write how the results are aggregated. And I have to write these two procedures. I mean, this is very, very simple. It just gives me back the state of this aggregator. So let's have a brief look at how this looks like. So this runs, and on each node, of course, I have a local function here that gives me, for a specific link, gives me the current load. So the local operation that is performed when an echo message arrives at the node, and this function is executed. The maximum load on that node is determined based on the load of the outgoing links here, the maximum load of the links connected to this node, and the link ID. So this is what's happening locally. Here it's what's happening if a child reports to a parent, and the parent processes the message. The child reports in what is the maximum load on the subtree the child is root of, plus the link ID of that carries this maximum load. And the processing is very simple. If this child load is larger than the max load which is currently stored on this node, then the max load becomes a new value, and also the ID of the link that carries this load becomes a new value. That's it. You're done. With this couple of lines, you have now a program that runs in a network. You don't need to have the knowledge of the topology. You just execute it, comes back, and gives you the link with the maximum load. Okay. Let me ask you the following. If I want to know the average load, not the maximum load, I want to know. I have all these links in my network. I don't know how many there are, but now I want to know the average load. How do I have to change this program? Where do I have to make a change? Here, huh? Yeah.
Children, then of course I have to divide by the number of children that send this message to me.
So I have to know the number of children, or can I just take the average?
We have to normalize this somehow.
Okay. So I have to say you're very smart, because most people give the wrong answer here. And I was actually hinting at the wrong answer. And because it's important, I want to show something important afterwards. And the wrong answer is that instead of the maximum load, I have here the average load, and then here you take the average load from here and the average load from here, and you average. And you're completely right. You cannot do this. You have to come up with something else. Okay. And so, why this is, I want to discuss, and then I show you the average load aggregator. Because fundamentally, I want to discuss here, now I have echo, I have these aggregators, what can I fundamentally do with this? What kind of operation can I fundamentally execute? And these are, I'm going to show you 3 types of operation. The most important operation you can use for echo for is for distributed polling. Distributed polling, the idea is like this. So you have n nodes in your network. On each of these n nodes, you have a local value. This can be a utilization of link, or can be an error rate, or can be anything, any state value. And now what you want to do is you want to monitor and aggregate that is essentially a function of these local values across the network. This can be a sum or an average or another statistical aggregate, but you want to monitor or poll the value of such a function. Okay, so that is the monitoring speak. If you use distributed system terms, then what in principle you want to do is you want to estimate the value. You want to do estimate the value of this function. Okay. People look a little bit perplexed, but it makes sense what I'm saying. No? No? You have to understand this, otherwise I cannot continue. So I have n devices in my network. Each device has a lot of local state variables. I just pick one. Okay, the current utilization of the CPU of this device. Now I want to compute a global function over all these things, like the sum or the average or another kind of distribution. Okay, and this function is f here. What echo allows me to do is to estimate such a function. In monitoring terms, in management, we call this also polling. I poll the network for this function. This is distributed polling. In a distributed system, people talk about state estimation, or they talk about snapshotting. All the same thing here. And so the question is now, what kind of function can I compute with echo? Can I compute all computable functions, or only certain type of functions? This is why is average possible or not? That was essentially the deeper question I asked. Huh? Okay. And so I have here 3 answers, and actually there's a 4th answer here I'm going to discuss. So if you have your global function, and you can decompose this function into binary functions, this global function f, you can compose this into smaller f's, and these functions are commutative and are associative, then you can compute f. Yes? Right. He doesn't have to change my batteries, he changed the batteries of the microphone. Right. Okay. The reason why we have these 2 conditions is because ECODAS is asynchronous processing, as we said. So the sequence of the argument should not matter. Whether I have 2 nodes, and whether this child node reports in before the other one or the other way around should not matter on the result. This is what this thing says. The other thing, this thing says that the structure of the tree should not matter for the result. And this we discussed. I just need a spanning tree. It doesn't have to be a BFS tree or just need a spanning tree. And so, if this is true, then I can compute. A simple example is sum. So obviously, x plus y is y plus x, and x plus y plus c is x plus y plus c. Since sum has this property, I can compute sum using echo. Okay, so now we come to average. Obviously, average is symmetric, but this is also associative. If you take average of 3, average of 4, 5, is this the same as average of let me see, average of 3, 4, 5? Is this the same? What is this? What is this? So what is the left side? 7.5. And the right side? Average of... What is the right side? 4.525. Okay, so average is not associative. So we cannot directly compute it. We have to come up with but there's hope. You see, because average can actually be computed using two sums. This, I guess, what you hinted at, no? I can sum up all my values, and then I have to normalize by the number of values I have. Okay, so this means if I want to compute average, I have to compute two sums. So my aggregator component has two components which I have to aggregate simultaneously. And then in the root, I can divide them, one or normalize it. And so this is exactly what we are doing here. This is exactly what I'm doing here. I sum up the number of children. I sum up the number of links. Okay, so the value of the aggregator essentially is a vector which has these two components. And once I have the global aggregates of these two components on the root, this is why I have this global method, I normalize. So what I did in this example, I have a non-associative function which I express by associate by associate functions. By functions which are associative, and so I can compute this. Okay, this is another way. If, for example, I know the values of xi, okay, I can compute the number of occurrences using tree-based aggregation, using echo. For example, I can estimate the histogram of the values, the distribution of the values. Okay, now here is something first surprising, because we have discussed what I cannot compute, and I tell you now I can compute all functions, all computable functions with echo. And the way I'm going to do this, how I'm going to do that? I have a very complicated function expressed in x1 to xn. And I tell you, I can compute them. I can compute this function with echo. Say it again. Right. But I would need a theory for that, and I don't have. I personally don't have one. Maybe you have one, then you show me. I would be interested. But there's a trick. And that is, you can in principle use echo just to collect all the XIs. Just to call the XIs and bring them up to the root node. And once you have them all lined up, you apply this function. Now this is a very strange aggregator, because what you're actually doing, your aggregator function is you add to a queue. No, you build up a queue of all, or you build up a set of all these values xi. But in principle, you can build an aggregator. The problem with that is twofold. Of course, the messages get longer and longer and longer in a large system. And the second problem is you have the same problem as a decentralized system. You bring everything to one node and process it then. So this is why while theoretically this is a possibility, in a little system you might not want to do that. This is why I'm not discussing this here. But there are many statistically interesting functions which you can compute with echo. And also database function, by the way, which you can compute with echo. So this is one thing. Echo is useful for global snapshotting, distributed polling. Here is a second area where echo is very useful, namely for network search. You have a very large system. You look for a resource. You run an echo algorithm, and for example, find a set of routers that run a specific version of iOS. I think everybody in this room within 5 minutes could write an aggregator which does this. So you write the local function essentially, check the node whether iOS is installed. This is all you have to do. Okay, and then the question is what you want to get out of it. Maybe you want to find out the number of nodes who have iOS x.y installed. You can aggregate that result, or maybe you want to know for the routers who have installed them their IP addresses. So you write an aggregator that bring the set of IP addresses to the root. Okay. You can also perform, and this is a third class of operation here. You can perform operations on node with given properties, and I have here also a very simple example. Also, this aggregator you write within 5 minutes, and then you have this function. This is actually not a trivial function which you can execute now in your network. And you can execute it on a network which the size of which you do not know, the structure of which you don't know. The only thing you need to have is a connected graph of your the connecting network graph. Okay. So this is about functionality. And the question is now, how does echo perform? What can I say about the performance of this distributed protocol when I run it on a network? As you remember, in the first hour, I talked about some metrics that can characterize, centralized managed function. We said how many messages are produced for the management traffic, what is the load of the management station, what is the execution time. The same we can ask here. What is the management traffic? What is the node on each load? Okay. What is the execution time? And how do these metrics, how do they change when I increase the system size? Because that's going to be of importance. Now, from the execution of the echo algorithm, we know that every node, every link to execution, every link carries two messages. One from left to right, and the other one from right to left. Okay, so so the overall load is going to be 2 times the number of links. So we know the messages. Okay. But look, this is but if I should look at the link, so I have 2 messages per link per execution. This is very interesting. It's a very interesting pattern for us because this is a balanced load pattern. Normally, if we do centralized managed operations, you do not have balanced load. You have bottlenecks. If you run echo, you have a balanced load. You have a balanced load in terms of if you just count the messages. It depends then on the aggregator. If you have certain aggregator, it can be that messages, they increase in the size when they come close to the root. Right. But in principle, if you just count the message, you have a balanced load in network. That's a very interesting property from a management point of view. And right, and also this load is independent of the network size. The load per link does not increase if the network size increases. It stays the same. The same happens if you look at the processing load on a link. The processing load on a link is dependent on the number of neighbors it has, so on the degree of the node. And you can also say it is bounded by the degree of the graph. The degree of the graph is normally defined as the maximum degree of a node. Okay, and you see also here, it's a very nice property. This property is independent of the network size. And you can control it by the number of neighbors you have when you construct the network graph. Yes?
One question. Does this hold for the information that is collected but cannot be aggregated? For example, some IP flow information.
Right.
So if they are not be aggregated somehow,
Right.
as they are propagating the root, they should increase in size.
Right. What I'm measuring here in network complexity is the number of messages. And so the number of messages does not change. The size of the message changes. Right. Right. So the question is what kind of aggregation you're doing. You can there's a specific term for that I just forgot. It's called semantic compression. Certain information essentially does not change in size when you send it up the network. Like if you count the number of nodes within certain bounds.
But of course you can compress.
Right. But if you are interested, for example, in the IP addresses of all nodes, and you want to collect them, then you concatenate. One way is to aggregate, to concatenate all these IP addresses and put them into a message and send them up. And there, of course, the closer the root comes, the larger the message size becomes. Right. That is not, this phenomena is not captured by this analysis here. You're correct. So we do not think about those examples when we think about when we try to discuss the benefits of this scheme. Just keeping that in mind. Right. Okay. So what can we say about the execution time? The execution time is one sees very easily that the execution time depends on the height of the aggregation tree. And the height is upper bounded by the diameter of the network. So the execution time increases or is bounded by the diameter of the network, and by the way, also the degree of the graph. Now, the diameter of the network, of course, is dependent on the system size, but also depends on the topology. If I have a grid network, two-dimensional grid, the diameter increases with the square root of the system size. For many topology with which we are using today, network topologies and overlay topology, the diameter increases with the logarithm of the system size. Okay? So I can choose a network graph such such that the execution time increases with the logarithm of the system size. Now it makes it, and this is what I just said here. Yeah? So here you can characterize the performance profile of an echo-based management operation. For the execution time, you have to assume upper bounds for network delay and processing delays. And you of course, you get these things, you get these properties from the properties of the underlying echo algorithm. Now, it's interesting to compare this with a centralized management operation, which we did in the first hour here. Remember, for a centralized management operation, all these metrics increased linearly with the system size. Okay. And this is why we call, by the way, echo scalable, because all these characteristics, they increase. They are either independent of the system size, meaning here the management traffic per link and the load on the management, they are independent, and the execution time goes with the logarithm of the system size, so much smaller than linearly. Now, this clearly shows that this protocol has a huge advantage when it comes to large networks over centralized management. And this advantage in real system, as I mentioned before, shows when you have in the order of 1,000 nodes. Below 1,000 nodes, you get many times better numbers using centralized management, now in real settings. Above 1,000 nodes, you get better numbers if you're using echo-based management. And the larger the system is, if your system size is 100,000, then the difference can be several orders of magnitude. Okay, so this about the performance. By the way, I missed one step because I was giving you the echo protocol, was giving you the echo algorithm, and I was telling you what research found out about the properties of the echo algorithm, and I just translated that into properties of the echo protocol. What I would have showed you that actually these two protocols are equivalent with respect to message exchange. And that needs to be proven. So in principle, that this is a theoretical proof that I would have to do. I would have to show trace equivalence that for every execution of the algorithm, there exists an execution of the echo protocol and the other way around. And then I can actually make all these claims. I just mentioned this for completeness, because this is a very long and boring task to do this. Okay, so I mentioned at the beginning, the protocol I'm showing you is somewhat of a skeleton. It is a full protocol. You can implement this code and it runs in your lab. But this is not sufficient if you want to run this in a real environment. And I have here a list of things which you would have to take care of if you would like to run this effectively in a real operation environment. The first is the point that Sean mentioned an hour ago. The code I gave you essentially limits a single execution of echo at a time. Now, of course, in the large system, we want to have many concurrent executions possible. Specifically, if we only read, if I have only read operations, then I can have as many execution as my system supports concurrent. If I do write operations, then I have to see which data I'm writing. But that's another issue. I can think of, if I have a very large system like today's internet with, I don't know, almost 1 billion hosts, that I would like to restrict the scope of echo. Because by definition, echo expands over the whole domain. Okay, and one logical way to do it is just say I restrict it to 5 hops, 10 hops, or whatever you want to initialize it with, and for example search in that area. So you would like to develop a version of echo that only goes for 5 hops or 6 hops. Right. Actually, this sounds straightforward to do, but when you start thinking about it, there is a catch. It is actually not so easy to do. Does anybody see why?
Because you don't know the network architecture.
Right. Yeah. I have. Yeah. I don't want only the professors. Yes, Benoit.
I can leave some students to answer, but that's okay.
I want to have the students.
There's no answer, I can try one.
Right. Okay, Benoit, please.
But in fact, the fact that the protocol is not synchronous.
Exactly. That's exactly the point.
The node that receive the message will receive it.
Exactly. It can actually happen that the node is visited twice. And then I get the wrong result. So the protocol is not correct anymore. So I have to extend the protocol that this doesn't happen. There are ways, of course, of doing the practical ways of doing it, but I have to take care of it. Okay. If I use echo for distributed polling, because a lot of management applications today are based on polling. So one can do distributed polling with echo. And if I have an infrastructure that doesn't change, stays the same for a very, very long time, I actually could come up with a more effective version, more efficient version by not for each run of echo, for each execution of echo, construct a tree again. Because what echo does is it constructs a spanning tree, knowing absolutely nothing about the network each time. So it would make sense that I construct a tree, I keep the tree, and just do periodic polling on the tree. Now, in such a solution, we must take into account that if we keep the tree, that the network actually might change during that time. The node might go down. And so you have to maintain the tree. You have to reconstruct the tree. Okay. The next point here, robust echo. So if you look at this execution, which shows just a part of the network here. So the root sends an explorer to this node. The node sends an explorer to its neighbors, except the root. Now, this node crashes. What's going to happen if I execute the protocol I showed you? Right. So this message, the echo message here would never reach the root. So the process here would not end. So the protocol I have showed you is not robust against node failure. And I have to think about ways how to harden the protocol. Okay. Right, so this is, and you see that there are more. Yes, Ramon.
I was wondering whether you or other people have been looking at those things from a wireless perspective instead of using wire links and reliable links that you never have an error. There is some works around that they have been trying to use this stuff for take advantage from that. So I don't know whether there is some works around that.
Right. We gave, this is an interesting question. We gave it some thought, but we did not do any systematic studies. And you're correct. These are exactly two of the issues that come up there. On the one hand, essentially, your neighbors are implicitly given by the range of your communication. This is number one. And number two is these links can be very unreliable. And message loss, for instance, is not covered in this protocol. Yes, that's true.
So when the node fails, then the spanning tree is again computed from the root.
The protocol I gave you, huh?
I mean the third point, because it must keep the spanning tree alive between runs.
Right. The point here is the following. Echo builds a tree every time it executes. And you can say this is a waste of resources. As long as if the underlying network doesn't change, why should I discover the network topology all the time and build a tree on top of it?
Depends on the frequency.
Exactly. And I'm saying, fine, then you build up the tree, and you let the tree, and you just pole along that tree. But something can happen in the meantime, and you have to have a mechanism that keeps the tree, that repairs the spanning tree. So you have to take care of this. Okay. So what did we say? We say we end 5:15, no?
Yeah, we basically the bus is going to pick us at 5:45 from the
Right.
to go to the square. I would say that some people can collect their stuff if we finish at 5:15, 5:20.
Okay, good. So then I have another 10 minutes. And so so this was one protocol I showed you, huh? And I wanted to say the important for me this is just a protocol skeleton. Essentially, it's a family of protocol, which you're going to adapt based on your operational needs. Then, and you can write aggregators according to your functional needs. And there's another family of protocols which we call GAP protocols, which are somewhat similar to these echo protocols. And I'm going to use this couple of minutes just to give you a flavor of this family of protocols. And if you're interested, you can read up the report and study them yourself. So this is what is characteristics of the protocol, and let's look at following in the following way to this protocol family. We know echo, and we try to find out what the difference is. Huh? Okay, so this protocol executes on a bidirectional connecting network graph. Echo does the thing as well, so there's nothing new. This provides a continuous estimate of a global aggregate computed over local variables. Now the difference is here, continuous. You know, but because what echo does, if you use it for monitoring, echo gives you a snapshot. Echo does polls a value, estimates a function in a point in time. Now what this protocol family does, it continuously estimates the evolution of an aggregate over time. Now you can say, I can do this with echo as well. I just poll all the time. This is not such a good idea. Why? Because in principle, this is the same difference as between polling and continuous monitoring. Why do I really need two different functions for that? Okay, so one, yeah, you must know that. So I use this protocol for distributed continuous monitoring. This is basically what this gap family does. And then, right, so, and okay, then you are saying I could use echo, but I have a lot of overhead because I have to poll all the time. Overhead is one, but there's something more fundamental which is different. So if you have an aggregate function, okay, and if you just poll aggregate that can change over time, you want to follow this, and you just poll values at distinct point in time. You might actually miss something important. You might poll, then this thing peaks. Okay, you poll again. You don't see anything. So for many management protocols that supervise something, for instance, it's very important that you catch these outliers. So you need to do continuous monitoring. You need to have a function that does not only polling, but allows you to continuously follow. And this is what this does. Okay? So, and this is actually a function which is echo in a real system is active only a very short time. You know? Even in a large network, the execution time of echo is very short. Normally sub-seconds, even if you have 10,000 nodes. Okay. This operation, if you do continuous monitoring, obviously this stays for a very long time. Now, if something is active for a very long time, things happen in a network. You might have node churn, new nodes coming, nodes leaving, nodes crashing, and your protocol has to deal with this. Okay, and as we know, such a protocol has two parts. One part essentially describes the message exchange. This is the underlying distributed algorithm, and one part is then the aggregator. Okay, the message exchange is message exchange on a tree, so you need a tree structure. And so what the specific problem here is that you create a tree, and you adapt this tree during changes in the network. On top of which, you can then do continuous aggregation. And there's a last thing which you have to do with this protocol, because we want to have this protocol executing in very large networks. If you have 1,000 nodes, if you have a million nodes, each node has a variable that changes once per second. And you want, at the root node, you want to follow an aggregate of that has as arguments, all of these local variables. You have to follow how many events on the root node per second? 1 million. You have 1 million events in the network. Okay, so you see here the scalability problem. You have somehow control the trade-off between the protocol overhead and the estimation accuracy. So you have to stop some of these messages. They're not going to get through, but so this means you're going to make an error. But what you want to do, you want to control the trade-off. You want a trade-off between, because if you have a lot of overhead, you have a lot of accuracy. You have a little overhead, your accuracy can go down. You want to control that. You want to understand and control that. So that is what you have to do in thing. And then this protocol is based on distributed algorithm that create tree. Here is the Bellman-Ford algorithm. Then we have a tree reconstruction algorithm here that helps to reconstruct the tree. And we have tree-based aggregation. So these are 3 distributed algorithms that underlie this protocol. And yeah, by the way, this is just how continuous monitoring works. And here executes the GAP protocol. Okay. And here's the description of distributed algorithm. Here is distributed aggregation. And here is now the code of this continuous aggregation protocol, GAP. 1 page, 2 page, 3 pages. That's it. And also here we can ask ourselves, what is the performance of this protocol based on the performance of the underlying algorithm. And we can ask ourselves, oops, there's something else. What is, oops, let me see here. And we can ask ourselves, how do I have to extend this skeleton to use the protocol in the operation environment? If you're interested in this, you can read it up yourself. And for fun, I have here 3 assignments because we are here in the summer school. And so the first is an echo aggregator. The second is extend echo to make it robust. And the third is actually is something very interesting. The GAP protocol gives you continuous update of global aggregate on the root node. Now you can ask yourself, sometimes actually I want to have it not just on one node, I want to have it on all nodes in the network. I want to know what the aggregate is. And of course there's a trivial way of doing this. You have it on the root node, I just broadcast it. Okay, but for many reasons this is not a good solution. But you can ask yourself, can I extend the protocol that such that I have it just on the root node, I have the aggregate on all nodes, an estimate of the aggregate. It turns out there is a very simple extension of the protocol that allows you to do that, just a couple of lines. Okay, so if you are interested in this and you want to make such solve such an assignment, you can send me a solution and I'm going to send you my comments. Right. Here is some basic literature. This is the